Welcome to this explainer. Today, we are going to take something that usually causes, well, let's be honest, a fair bit of anxiety, an 80-question test, and transform it into a really clear conceptual journey. We're doing a comprehensive review of the key chemistry concepts from the grade 12 model examination. We're talking atomic models, periodic trends, chemical bonding, stoichiometry, acid-base equilibrium, the whole shebang, all the way to electrochemistry. But hey, we aren't just going to read out answers here. We're going to completely unpack the science behind them, traveling from the tiny, microscopic behavior of subatomic particles all the way up to those massive industrial processes that literally shape our modern world. So if you've ever felt a little overwhelmed by the sheer volume of chemistry concepts out there, take a breath, because you are absolutely in the right place. Okay, so here is the game plan. We've organized this into a logical building block structure. We'll kick things off with atoms and periodic trends, then we'll see how those connect in chemical bonding and structure. After that, we set them in motion with reactions and gases, find a little balance with acid-base and equilibrium, and finally, we scale it all the way up to the real world with electrochemistry in action. Let's dive in. Section 1. We are starting right at the core of it all, the microscopic foundation. Because to really get anything else in chemistry, you've got to master atomic theory and understand exactly how elements behave and are organized on that periodic table. Let's test your knowledge right out of the gate with one of the most famous experiments in scientific history. Think back to Ernest Rutherford. Do you remember what he actually discovered when he shot those positively charged alpha particles at an incredibly thin sheet of gold foil? Because at the time, scientists just assumed atoms were this diffuse, mushy plum pudding of positive charge with a few electrons sprinkled in. So what did Rutherford actually see? Well, it turns out atoms aren't solid at all. While the vast majority of its alpha particles passed straight through that foil like it wasn't even there, a tiny fraction bounced right back. And that led to a totally groundbreaking conclusion. Atoms have a super dense, positively charged center. Most of the mass and literally all of the positive charge is packed into this tiny nucleus, while the rest of the atom is just empty space. That revelation completely shifted modern chemistry. Now, what's really cool is how we use isotopic data from the exam to mathematically prove average atomic mass. Say we have an unknown element X with two isotopes. You've got X40 making up 80% of the element in nature and X44 making up the other 20%. To find the average atomic mass, you can't just add them up and divide by 2. No way. You have to weight them by their natural abundance. So you multiply 40 by 0.80, giving you 32. Then multiply 44 by 0.20, which gives you 8.8. Add 32 and 8.8 together, and boom, you get exactly 40.8 U. It's a perfect reminder that the numbers you see on the periodic table aren't just random. They are beautifully weighted averages of reality. Section 2. Let's see how all of this builds as those individual atoms start connecting, sharing, and stealing electrons to form complex molecules. Okay, the exam throws a fantastic curveball at us here about how atoms bond. We're taught super early on that atoms just want to achieve a nice, stable set of 8 valence electrons, right? But take a second to think about which of these structures, nitrogen trichloride, carbon tetrachloride, carbon dioxide, or chlorine dioxide, actually breaks those fundamental rules of bonding. Drumroll, please. The exception is ClO2, chlorine dioxide. But why? Well, it all comes down to the math. It contains an odd number of total valence electrons. Chlorine brings 7 to the table, and the 2 oxygens bring 6 each, giving us a grand total of 19 valence electrons. And you simply cannot pair up 19 electrons to give every single atom a perfect octet of 8. It's impossible. There's always going to be a radical, a single, lonely, unpaired electron left over. Chemistry loves a good exception to the rule. Moving right along to Section 3. Now that our molecules are built and bonded, let's look at what happens when they smash into each other, react, and exchange energy. Welcome to the dynamic world of stoichiometry and kinetics. When we look at chemical reactions, we absolutely have to contrast 2 fundamental types of energy flow. Think of endothermic reactions as giant energy sponges. They actively absorb heat from their surroundings, which actually makes the environment cooler. Their enthalpy change, or delta H, is positive. On the flip side, exothermic reactions are like a roaring fire. They release heat out into the surroundings, so their enthalpy change gets a negative value. Grasping this energy flow is literally the foundation for designing everything from instant cold packs to massive rocket engines. And speaking of reactions, let's talk about speed.
The exam brilliantly illustrates how we write a valid rate expression based on the change in concentration of a gas over time. The reaction is 2 moles of NO plus 2 moles of H2, producing 1 mole of N2 plus 2 moles of H2O. If we want to express the speed of this reaction specifically in terms of nitrogen gas, which is our product, we look at the change in its concentration, represented by that delta symbol, over the change in time. Since nitrogen is being produced, its concentration is going up, meaning the mathematical expression is positive. It's a really simple ratio that tells us exactly how fast our chemical factory is running.
All right, section 4. Next up, we are tackling a massive pillar of grade 12 chemistry, equilibrium. This is all about systems that aren't just a one-way street, but are constantly trying to find a perfect, dynamic balance between reacting and unreacting. To conquer this middle chunk of the exam, you absolutely have to have these core concepts locked down. You need to confidently calculate pH and pOH, which are really just inverse scales, telling us the hydrogen and hydroxide ion concentrations. You've got to understand Le Chatelier's principle, which is basically how a system at equilibrium pushes back when it gets stressed out. But perhaps most importantly, you need to deeply understand buffer solutions. Buffers are amazing. They are special mixtures of weak acids and their conjugate bases that actively fight against dramatic changes in pH. Without them, biological systems, including the very blood pumping through your veins right now, just couldn't function. Let's look at a specific mathematical scenario from the exam. We need to determine the equilibrium constant, or Kc, for the dissociation of N2O4 into 2 molecules of NO2. Imagine we start with exactly 1 mole of N2O4 in a 1-liter container, and a certain amount, let's call it X moles, breaks apart. That means we are left with 1 minus X moles of our reactant. But because of the stoichiometry, where every one molecule that breaks apart creates 2 molecules of product, we end up producing 2X moles of NO2. So plug that into our equilibrium formula, which is always products squared over reactants. We take 2x, square it to get 4x squared, and divide it by the remaining reactant. That gives us our beautiful final equilibrium expression, 4x squared over 1 minus x. Finally, section 5. We are scaling things up to the macro level. We zoomed in on atoms, bonds, and reactions, but now let's explore how these invisible electron transfers actually drive the massive industrial processes and technologies all around us. The exam highlights a really vital and honestly quite surprising distinction about how things conduct electricity. Think about a simple copper wire. That's metallic conductivity. As that metal heats up, its atoms vibrate more and more, effectively getting in the way of the flowing electrons. So metallic conductivity actually decreases as the temperature goes up. But now think about salt water, an electrolyte. When you heat up a liquid electrolyte, it becomes less viscous, less thick, meaning those charged ions can suddenly move around way faster and much more freely. So electrolytic conductivity actually increases with temperature. 2 different systems, totally opposite behaviors. Okay, this next topic is fascinating because it steps right out of the textbook and into a real-world factory, asking about the preparatory stages of leather tanning. It's one thing to balance chemical equations on a whiteboard, right? But it's a whole different ballgame to know how these chemicals are actively applied in industry to preserve and transform natural biological materials. The sequence the exam tests perfectly outlines the brutal chemical and physical steps required to prepare a raw hide. You have to start by curing it, usually with salts, just to stop decay. Then you soak it to rehydrate the material. After physical flush removal, you bring in specific chemicals, like lime, to chemically burn away the hair. Then comes scudding to physically squeeze out impurities, and finally, deliming, which neutralizes and removes those incredibly harsh alkaline chemicals before you can even begin applying the actual tanning agents. It's a rigorous process, but it perfectly showcases chemistry's incredible practical utility. The exam places heavy emphasis on these industrial processes, and for very good reason. They are literally the chemical backbone of modern civilization. You have the Haber-Bosch process, which pulls nitrogen out of thin air to create ammonia. This is the fertilizer that quite literally feeds billions of people today. Then there's the contact process for manufacturing sulfuric acid, which is arguably the single most important industrial chemical on the planet. And let's not forget polymerization, creating marvels like Teflon, the nonstick coating we use in our kitchens every single day. These aren't just abstract exam questions. These are the core chemical reactions that built our modern world. I want to leave you with a really provocative thought to wrap things up. We've talked about all these amazing, massive industrial processes, but the reality is they often produce a lot of waste. The core principle of prevention in green chemistry completely challenges us to rethink this. It demands that we design our chemical syntheses to eliminate waste from the very beginning, right at the drawing board, rather than just trying to clean up toxic byproducts after the damage is already done. So as you master all these incredible building blocks of chemistry, remember that the real test isn't just passing this exam. It's asking yourself, how will you use this knowledge to design a cleaner, much more sustainable future? Keep that in the back of your mind, keep studying those structures, and I'll catch you on the next explainer.